Well, thank you, Vicki. It's a pleasure to be here at the Museum of Mathematics tonight to talk about Newton. This is Newton. So this is our protagonist. This portrait is called Newton in His Own Hair. No wig on this one. Now, there's various ways you can approach Newton, but what I've done is this. I've gone to the correspondence of Isaac Newton, which was published by Cambridge University Press, and I've read all his letters. So this covers 3,000 pages and 7 volumes. And then what I've tried to do is pick some of the greatest hits from Newton's long correspondence that I hope will reveal something of his character and a little bit of his mathematics. There'll be a section of some of his letters from Cambridge, where he was both student and professor. There'll be some letters from London, where he was a parliament member and worked at the Mint. There will be some letters regarding the priority dispute, which you may know about, this great battle between Newton and Leibniz over which of them deserves most credit for founding the subject called calculus. And I'll end with his most famous passage, I think, where he talks about standing on the shoulders of giants from one of his letters. So let's begin. There's a long list of things to do. Let's start with letters from Cambridge. Cambridge was where he was a student in 1661. He went up to Cambridge, as they say. This is Trinity Great Court at Cambridge. And if you've been to Cambridge, this is one of the most beautiful spots in the world. It's really spectacular. This picture was taken in the 20th century, but this is what it looked like when Newton was there. His earliest letter was written in the year he went up to Cambridge, 1661. It was to a friend who had been reported inebriated. So Newton was told that your friend was drunk, and Newton felt obliged to write this friend the letter. I earnestly desire you first to repent of your having been drunk, says Isaac, and if it please God that you ever be well again, then have a care to live healthfully and soberly for time to come. So right from the get-go, he's a scold, right? And not your typical frat boy, right, in terms of drinking matters. But this is Newton. He was a Puritan from start to finish. That's obvious. The years 1665 to 67, when he's a student at Cambridge, are called his Anni Mirabiles, his miraculous years. Because during this time period, he does extraordinary things that are almost mind-boggling in terms of their scope and depth. He gives us the generalized binomial theorem. And I'm going to show you that one. That'll be our piece of mathematics in a few minutes. He also invents something called fluxions. Now, we call that differential calculus. Not bad. And he invents inverse fluxions, which we call integral calculus. Not bad. And he works on the laws of motion, and he works on optics. He's essentially here charting the course of modern science and mathematics. But what's so amazing is he's doing it as an anonymous student at Cambridge. Nobody knew what he was up to. He hasn't published this stuff. Just in his notes, he's done just extraordinary things. It's been said these may be the most productive 2 years that any human being has ever had. How did he do it? Well, he said later, well, I thought upon these matters continuously. I just thought about them all the time. There are reports of a colleague going by his office in the evening, his rooms in the evening. And there sits Newton, a big stack of paper, his quill, candles high. When the friend comes back in the morning, Newton hasn't moved. The papers have been filled with mathematics and the candles have burned low. He just worked all night. He would forget to sleep. He would forget to eat. He was so immersed in this quest. And it's said that his cat grew fat, eating his untouched meals. Now, during this time, this passion for learning took strange forms, and later he recalled one of these when he was experimenting with vision. And I should say that in those days, vision and light and color were all sort of the same subject. You know, that nowadays we split vision off and put it in the biological sciences, and light is sort of physics. But then it was all sort of one big thing, and Newton was interested in this, so he thought he would do an experiment upon himself. He said, I looked a very little while upon the sun in a looking glass with my right eye, and then turned my eyes into a dark corner of my chamber. So he's got a mirror. He's looking at the sun until he couldn't stand it anymore. And then he looks in the dark room to see what happens. Wow, he says, there's flashes of purple and orange. It's just amazing what happened. But then he went on and reported that by keeping in the dark and employing my mind to other things, I began in 3 or 4 days to have some use of my eyes again. This is what he would do to himself. It's very dangerous. Do not do this. But even more famous is this thing, and you might have seen this before. This is a passage from his notebook. Again, he's experimenting with vision. And he tells us here that I took a bodkin. Now, a bodkin is a little sharp knife. Think of a nail file. Okay. So I took a bodkin and put it betwixt my eye, and the bone as near to the back side of my eye as I could. So he's taken this nail file and stuck it behind his eyeball. And here's his hand, and here's the bodkin, you see? And then he said, and pressing my eye with the end of it, so now that it's back there, so as to make the curvature of my eye, A, B, C, D, E, F, and there's A, B, C, D, E, F, there appeared several white, dark, and colored circles, R, S, and T. And here they are up here. There's the circles. And he says, as he presses this thing behind his eye, the circles would get bright, but if he held it still, they'd fade away until he started rubbing again. So this is Newton, right, in his passion for learning. Do not do this at home, as they say. I can't prove it, but I think at this point, his cat grew queasy. Probably. Okay, so Newton. Now, while he's doing all this, he's not telling anybody. Remember, he's anonymous. And he writes a letter to John Collins in 1669 in which he sort of gives his philosophy of fame. He says, I see not what there is desirable in public esteem were I able to acquire and maintain it. It would perhaps increase my acquaintance, the thing which I chiefly study to decline. If he became famous, his acquaintances would go up. And then what? He'd have to write letters and talk to people and stuff instead of doing his wonderful physics and sticking bodkins behind his eyeball and stuff. So he was not interested in fame, says he. And in fact, he was pretty much anonymous. So it's kind of amazing that that same year, he becomes the Lucasian professor of mathematics at Cambridge. This was the most prestigious mathematical chair at the university. And one of the questions is, how did this happen? How did this unknown person get this great chair? And it seems to be that what happened was he was not completely unknown, because the previous occupant of this was named Isaac Barrow. And Barrow had been a mentor to the young Newton. And Barrow knew that this guy was something else. And when Barrow was ready to depart the chair, he recommended that the unknown Newton fill it. Barrow said that Newton was a fellow of our college and very young, but of an extraordinary genius and proficiency in these things. And with that recommendation, Newton becomes Lucasian professor. His responsibilities in this chair are very few, but he did have to give public lectures every once in a while. And we have firsthand reports of these, and apparently he was terrible at this, because the report said that so few went to hear him, and fewer yet understood him, that he oftentimes did in a manner for want of hearers read to the walls. And the story is that he had to give the lecture. That was in the contract, even if nobody came. And so he would read to the walls. Now, think about it. Suppose Isaac Newton were speaking tonight at the Museum of Mathematics. What a crowd he could draw. But when they actually had the chance to hear him, they didn't go. So, in 1671, he invents the reflecting telescope. Just one of the many crumbs from this great feast that he gives us. And if you know about telescopes, there's sort of the two species, right? There's the refractor, the tube with the lens at the end. That had been Galileo's type. But then Newton invents the reflector, which has the mirror at the bottom. And he figures out how this should work, what the optics should be, and he actually makes one. He was very good with his hands. He had to grind the lens and build a little tube. He does. That's his drawing. And he sends it down to London to the Royal Society, which was the great scientific body of its day. And they receive this from this guy, Newton, up in Cambridge. They love it. This reflecting telescope works great. And they make him a member of the Royal Society. So this was his first public splash. And apparently he was sort of encouraged by the reception. So he says, now I'm going to send them some of my optical papers, which he had been working on. So he sends down to the Royal Society some of his theories of light and color. But these were not received so enthusiastically. There was criticism. There was questions. And the leader of this criticism was Robert Hooke, who was at that time the big cheese in London in the scientific body that was the Royal Society. And you might have heard of Hooke's law in physics. That was that Hooke. So Hooke criticizes Newton's theory. I don't agree with this. I'm going to challenge you on these points. And what's supposed to happen in science when you send in a paper and somebody criticizes, then you rebut them, and then they rebut you, and you try to either prevail or else you reach some sort of middle ground. Not Newton. He says, all right, you're going to criticize me? The heck with you. I'm not sending you anything else. If you don't like it, tough. And in fact, he decided he wanted to resign from the Royal Society. I desire that I may be put out from being any longer fellow of the Royal Society, he writes. I could wish I had met with no rudeness. Now that rudeness, it seems, is what is just normal criticism, but he has a very thin skin, and he just was going to resign. Now he didn't resign, and in fact, late in his life, he becomes the head of the Royal Society for decades. But at this point, he very nearly bailed out on him. In the 1670s, he undertakes some correspondence with the great German mathematician Gottfried Wilhelm Leibniz. And this is going to be evidence in the case we're going to bring about the calculus wars. But let me just mention what they were. Newton writes to Leibniz in June in the first letter, the Epistola Prior, the early letter, in which he explains to Leibniz about the generalized binomial series, which I'm going to show you in just a minute. I keep promising that. Leibniz writes back in August, very impressed and sharing some of his mathematics with Newton. And Newton writes a second letter, which is now called the Epistola Posterior, in October. And that was it. At that point, Newton said, I hope this will so far satisfy Mr. Leibniz that it will not be necessary for me to write any more on this subject. I have spent too much time writing letters to this guy. I got other things to do. But that will, just watch how this plays a role in what's coming. But let me now divert and talk about this generalized binomial series that Newton was so proud of. And this is the Museum of Mathematics, so this is the math part here. Some of this you might know depending on your background and training. Maybe you haven't seen all this. So let's just take a look at this. This is one of his first great discoveries. See if you think this is genius in action. Now, a binomial means two terms, like 1 plus x. That's a binomial. And in high school, you do things like squaring that. So 1 plus x squared means 1 plus x times 1 plus x, of course. And then the FOIL method. You multiply these together, and you get 1 plus x plus x plus x squared. And when you combine the two middle terms, it turns out to be 1 plus 2x plus x squared. So if I wanted to square 1 plus x, that's what you get. Everybody knows that from their high school. But what if you wanted 1 plus x to the 17th? Now this is a way harder problem. You don't want to multiply 1 plus x, 1 plus x, 1 plus x 17 times, or it'll be Thursday before you finish this. So you'd like a shortcut. And the shortcut shows up in what's called the binomial expansion. So if I want 1 plus x to the power r, then this turns out to be 1 plus rx is always what you get next. Then you get r times r minus 1 over 2 times 1, and that's how many x squared you get. And then the pattern goes r times r minus 1 times r minus 2 over 3 times 2 times 1 x cubed, and so on, and so on, and so on. And that's called the binomial expansion. And you can see this working. Let's say we let r equal 2. Let's say I want to do 1 plus x squared, not by the FOIL method, but by this. So r is 2, and you'll get 1 plus 2x. The next term will be 2 times 1 over 2 times 1x squared. The next term will be 2 times 1 times 0 over 3 times 2 times 1x cubed. The next would be 2 times 1 times 0 times minus 1 over 4, 3, 2, 1, x to the 4th, and so on. But what happens here? If there's a 0 in this, it cancels. And there's a 0 in the next one, and the next one. All of the rest of these are going to just drop out because that 0 hits. And so all you're left with is this. And of course, if you cancel the 2 times 1 over 2 times 1, you get what we knew we'd get, 1 plus 2x plus x squared. So there it is operating when r is 2. Works. Okay. Now, suppose you want r equals 17. That is, you want 1 plus x to the 17th power. Now, all you got to do is put 17 in there where the r is, and you'll get it. And so it'll look like this. 1 plus 17x. Here comes 17 times 16 over 2 times 1, x squared. 17, 16, 15 over 3 times 2 times 1, x cubed, and so on and so on. And then you just have to do the little arithmetic to clean up these coefficients. And here's how it starts. 1 plus 17x plus 136x squared plus 680x cubed. And it'll march along until you get 17x to the 16th, and then an x to the 17th, and after that, all the terms disappear. So it just runs to that point and stops. It's a finite series. Now, if you're in school, you've seen this, and if you were in school, you've probably seen this somewhere, depending on your math training. But it seems to me there's always some kind of question like this. They say, if you took 1 plus x to the 17th, how many x cubes would you have when you're all done? You know, and if you know this formula, you know it's that. You just have to do 17, 16, 15 over 3 times 2 times 1, clean it up, and you say 680, and you got it instantly. So that's a neat theorem. Okay. Hey, one little thing before I get to Newton's contribution. Notice here we have 2 times 1, 3 times 2 times 1. There's a notational convention that mathematicians like. If you have something like, say, 4 times 3 times 2 times 1, you don't want to write 4 times 3 times 2 times 1. So you write this, 4 with the exclamation point. And what do we call this? Everybody knows 4 factorial. Yeah, that's what mathematicians say. 4 factorial. It's just easier to write. This is how you tell the difference between a mathematically trained person and a non-mathematically trained person. The mathematically trained person looks at this and says 4 factorial. The non-mathematically trained person looks at this and says 4! Okay. All right. So anyway, with that convention, then my expansion looks like 1 plus rx plus r times r minus 1 over 2 factorial, x squared, r minus 1, r minus 2 over 3 factorial, x cubed, and so on. So there's the way you might have encountered this. All right. So let me put that up there. Now, everything I've said so far was not new to Newton. 2nd power, 17th power, that wasn't so cool. What he said was this. That this is going to be valid even if that r is not a whole number. You don't have to restrict yourself to 2 or 17. And he writes and says, this is going to be good even if r is integral or, so to speak, fractional, whether positive or negative. And that is the insight that gives us what's called the generalized binomial series. Okay, so I'm going to show you an example of this in a minute, but just because my example involves fractional exponents, real quick to make sure we're all on the same page here, remember what these are. If I have 8 to the fraction 1/3, what is that? Cube root, yeah, so this is just a root. So that's the cube root of 8 or 2. Okay, so fractional exponents, we know what they are, they're roots. Well, here's my formula, one last time, and now I want to expand, as Newton did, the cube root of 1 plus x. I want to expand this. So what that requires me to do is write this as 1 plus x to the power r, but now r is 1/3, the fraction. But that's okay. Newton says this is good, even if r is 1/3. Okay, so let's see what happens. If I put in 1/3 for r all along here, this is what I get. 1 plus rx is now 1/3 of x. And then r times r minus 1 is 1/3. And then if you drop down 1, you get 1/3 minus 1 over 2 factorial. The next one will be 1/3, 1/3 minus 1, 1/3 minus 2 over 3 factorial, x cubed, and on and on and on. And that's the expansion of the cube root function of 1 plus x. So there it is. I'll put it up on the top. And now what you have to do is sort of figure out what these things are. What's 1/3 minus 1? If you go down 1 from 1/3, you go to negative 2/3. 1/3 minus 2 is negative 5/3. 1/3 minus 3 is negative 8/3. So here comes this expression when I clean this up a little bit. And then you just do the canceling and get rid of these fractions. And here's what emerges. 1 plus 1/3 of x. This guy turns into be minus 1/9 of x squared. this turns out to be minus 10 over 243 of x cubed, excuse me, plus 5/81 of x cubed, minus 10 over 243 x to the fourth, and so on. But notice what's happened here. This time, you get an infinite series. You never get that 0. Remember that 0 came in when we 2, 1, 0. But here, you skip over 0 from 1/3 to minus 2/3, and you'll never get back to it. And so this just goes on forever, an infinite series. And so this is what Newton has concluded, that the cube root of 1 plus x spins out into that. 1 plus 1/3 of x minus 1/9 of x squared plus 5/81 of x cubed. You know, and I look at that and I see nothing intuitive about that. Without this rule, I would never guess that you need minus 10 over 243 x to the fourth here to make this work. But that's what you need. And he checked it this way. And if you want to go home and do something afterwards, he took this series and cubed it. He took the series, multiplied it by itself, got a series, multiplied again by itself, and you know what comes out? 1 plus x. That's it. If you cube this series, everything else cancels. So if the series cubed is 1 plus x, what's the series? It's cube root. So there you go. So that was kind of neat. But then he wasn't done yet with this, because he now tells us that the extractions of roots are much shortened by this theorem. He's going to use this now to do something practical, and that is find roots. So suppose I want the cube root of 140. And now here would be my challenge. Suppose I say, I'll give you a stack of paper and a pencil and 5 minutes. And you've got to do the cube root of 140 to 5 places without a calculator. You know, so everyone would run away and screaming. And how can you possibly do this? Newton could do this because he has this series. Now, the one thing he has to observe, though, is that if you want this to work, the value of x that you put in here has to be small in order, as we would say, for the series to converge, to zero in on something. And you can sort of see this in just, if you think about it, if you have a big number, x, like 20, and you start cubing it and taking it to the fourth power, it's going to get huge, and the series kind of meanders about. But if you have a small number, like a half, and you square it, it's a fourth. And you cube it, and it's an eighth, and these numbers get smaller. And so the trick is, don't use this unless your x is small. Less than 1 is what Newton realizes. So that's not going to work. If I say I'm going to do the cube root of 140 and write it 140 is 1 plus 139, then the x is 139. That's too big. When you take powers of that, it'll go off the charts, so that's not going to do it. So Newton says, all right, here's what you do. You use artifice, his word, trickery. All right, so we're going to be tricky about this. So watch how he attacks this. Still, here's his big formula. He says the cube root of 140, I'm going to write this. I'm going to write 140 is 125 plus 15. Okay, so now, question 1, is 125 plus 15 140? Yeah, okay. Question 2, why did he pull out 125? Well, it's a perfect cube, yeah. So he's picking a perfect cube near 140. All right, now, under the radical, factor out 125. And you'll be left with 1 plus 15 over 125. You can see that's right. If you just multiply back, you get right where you were. Break this into the cube root of 125 times the cube root of 1 plus 15 over 125. Now, the cube root of 125 is 5. 5 times 5 times 5 is 125. So there, that's easy. And this other piece, I can reduce this to 3/25. If I cancel, divide a 5 out, that's going to be my x. 3/25. That's small. And when I take powers of that, it's going to converge fast. So that's the artifice. So now, let me finish this up and see what you get here. The cube root of 140, according to Newton, is 5 times the cube root of 1 plus 3/25. The x is the 3/25, so I go up here and put 3/25 in for x. So I get 1 plus 1/3 of x, now it's 1/3 of 3/25, minus 1/9 of 3/25 squared, plus 5/81, 3/25 cubed, and I stop because I'm tired at that point. So I don't, this is an infinite expansion, but I stop there, so I say this is approximately equal. Now, how good is it? Well, you do the math inside the square brackets. You know, like you could cancel, you know, these 3's, and you get a common denominator. So that's what you get the 5 minutes for, you know, to do this problem by hand. And it turns out that it's 5 times the fraction 9736 over 9375. Cancel the 5, and you get 9736 over 1875 is my Newtonian approximation of the cube root of 140. Now, is that any good? Well, now I allow you to get out your calculator. And I punched in 9736 over 1875, and it came out to be 5.19253. Now I got my calculator and put in the cube root of 140. And according to my calculator, that's 5.19249. I'm off 4 places in 100,000. That is good. And it only took me 4 terms to do it. It's amazing. But what's amazing is I knew which 4 terms to look at, and that's thanks to Uncle Isaac here who gave us this. So the extractions of roots are much shortened by this theorem, you bet. And notice that although this was the cube root, I could have done the square root, or the 5th root, or the 7th root just by changing the r to 1/2 or 1/5 or 1/7. Any root will fall to this. So I like that. Now he later wrote to somebody and said, I'm ashamed to tell you to how many places I carried these computations, having no other business at the time, for then I took really too much delight in these inventions. So maybe I should have been doing something more productive, like watching TV or something. But this is what he was doing. Okay, so that's my little math part. So I don't know. I think he qualifies as very smart if he can do that. Let me get back to some of his correspondence. In 1682, he writes a letter to William Briggs saying, I am of all men grown the most shy of setting pen to paper about anything that may lead into disputes. I don't want to get into disputes. I'm the most shy of any man. Okay. A few years later, he hears from Edmund Halley of comet fame. Writing from London, Halley says that regarding the inverse square law of gravitation, Robert Hooke, down in London, is claiming priority and wants to be recognized in the Principia that Newton's writing. So, a little bit of background here. What's going on? The inverse square law is this key idea of the way gravity works, according to Newton, that the force of gravity is inversely proportional to the square of the distance between the items. So if you're 3 times as far away, you only have 1/9 the gravitational attraction. This was the cornerstone of his theory of gravity. Upon this, he builds celestial mechanics. He builds what he calls the system of the world. This is the headline. And he's writing this book called the Principia that's going to explain all this. And now he hears that Robert Hooke says, Robert Hooke invented this, and you need to give me credit in the Principia. Now, Newton has grown the most shy of getting into disputes, but wait a minute, he has to write a letter to Halley about this. And Newton says, now, is not this very fine? Mathematicians who find out, settle, and do all the business must content themselves with being nothing but dry calculators and drudges, and another that does nothing but pretend to grasp at all things must carry away all the invention. Hooke is just pretending to have given the inverse square law. He sends this to Halley, Newton does, and Halley writes back immediately and says, Sir, I must now again beg you not to let your resentments run so high. But Newton's resentments would run high very easily. So, a little exchange here between Newton and Halley. Now, the next year they published the Principia. This is it. This is the title page. And let's guess. In this book, does he give Robert Hooke credit for the inverse square law? No, he does not. Right? This is Newton's masterpiece on celestial mechanics, on the way the universe operates. As I say, he says, I'm going to tell you the system of the world. It's been called the greatest science book ever written. And it might be. And it seems to me the only competitor it would have would be Darwin's Origin of Species. And what one does for the physical world, the other does for the biological. And what's really cool about this is Darwin also went to Cambridge. This little university town up in East Anglia has given us so much. Well, the book came out, and Newton got a review from a colleague, David Gregory, who wrote to Newton about the Principia and said, your book is of so transcendental fineness and use that few will understand it. What a review. This reminds me of Yogi Berra, who said that restaurant is so popular nobody goes there anymore. It's that same kind of logical strangeness. But anyway, that's the Principia. Okay, now, major change. Newton goes to London as a member of Parliament in 1688. Now, this leaves you scratching your head. If you think about U.S. politicians and how they like people and are warm and fuzzy, and Newton didn't like people and wasn't, how in the world did he get into Parliament? And the answer in part is this, that in England in 1688, that year, they had what's called the Glorious Revolution, where James II, the Catholic king, is forced out. And William and Mary, the Protestant monarchs, come in. And Newton was anti-Catholic. He was Puritan, pro-Protestant. This was the home team, and he wanted to go and support them in Parliament. So he stood for election in Cambridge and won and went down to Parliament. Later, he ran again and lost. So he just had one term. And his impact wasn't particularly great in terms of a legislator. Here's one letter. He did do something, apparently. He says, "This day, upon a motion made by Sir Thomas Clarges for Oxford and by me for Cambridge, the House of Commons gave leave to bring in a bill to settle the charters and privileges of the universities." So he was taking care of his university commitments. But other than that, his legislative footprint was not very deep. Okay, 1693 is Newton's black year. Somehow he descends into some kind of depression. And this is evident in the letters. He writes to Samuel Pepys, the diarist, in September, and says, "I am extremely troubled at the embroilment I am in, and have neither ate nor slept well this 12-month, nor have my former consistency of mind. I must therefore withdraw from your acquaintance and see neither you nor the rest of my friends anymore." So he's just backing away. And Pepys writes to somebody else, "What's going on with Isaac?" Because Newton had met some people when he was in Parliament. He actually was starting to expand his repertoire of friends, but here he's saying, "I'm leaving." Now, a few days after that, he wrote a really amazing letter to John Locke, the philosopher. Newton said this, "Being of opinion that you, John Locke, endeavored to embroil me with women, and by other means, I was so much affected with it, as that when one told me that you were sickly and would not live, I answered, 'Twere better if you were dead.'" Can you imagine getting a letter like that? When I heard you were sick, I kind of wished you died. Okay, well, that was Newton. It was in a bad mood. Now, sometime later, he snaps out of it and writes back to Locke and apologizes. He says, "This last winter, by sleeping too often by my fire, I got an ill habit of sleeping and a distemper, which this summer has been epidemical." And so he apologizes, and later in his life, he never has such a black period descend upon him again. Now, people have subsequently tried to figure out what was this, what was going on here. And, midlife crisis was about the time. His mother had died sometime earlier. Maybe it was a depression based on that. But one very intriguing theory is this. He was doing a lot of alchemy at this point. And the way he would test whether his chemicals were pure is he'd taste them. So now you just got a shipment of mercury in here. Let's see, is that good? Oh, that's good mercury. You start eating this stuff. Well, that could poison you. That could affect your brain. And maybe that's what he did. Now, if you think it would be ridiculous for him to be eating chemicals, this is the guy that stuck the bodkin behind his eyeball. So eating chemicals was nothing by comparison. But in any case, he finally gets over that. And then another major change. In 1696, he becomes warden of the mint. He becomes a public servant, goes down to London to run the mint, which at that time was in the Tower of London. That's where they would make the coins. And he was in charge of the recoinage. He had to work with the bankers. He had to work with the government. And he was very good at this. He was a very good administrator of the mint. Now, one of his responsibilities in this position was to go after counterfeiters. And he did. And there's a famous case with the counterfeiter named William Challoner. Challoner had been, I call him sort of a celebrity criminal. He had done counterfeiting, but he always got off, and everybody sort of liked him. He was friendly and, all that. And so he was, I read somewhere he counterfeited the Birmingham groat which was some piece of money or something. And he got off on that one. He got off. So now Newton comes in. He's not going to get off. Newton goes after him. He oversees the investigation, the trial. Challoner is found guilty. He's convicted and is scheduled to die. And Challoner now, the clock is ticking, and the only person that can save him is Newton, the warden of the mint. So he writes to Newton and says, I am going to be murdered unless I am rescued by your merciful hands. Oh, I hope God will move your heart with mercy and pity to do this thing for me. I am your nearly murdered humble servant, William Challoner. And he sends this to Newton, his last hope. And Newton ignores it entirely. If he's looking for mercy, he's in the wrong place. 16 days later, he goes to his death. So Newton was not your warm and fuzzy guy. Okay, now let me start talking about the priority dispute, this famous episode between Newton, here on the left, and Gottfried Wilhelm Leibniz on the right. This is called Leibniz in somebody else's hair. So the big issue here is going to be who gets credit for the calculus. So let me just remind you that in 1676, Newton had written to Leibniz the Epistola Prior, the Epistola Posterior, discussing some mathematics. That same year, Leibniz was in London. He was a diplomat, and he was over on a diplomatic mission. But while there, he said, hey, what's going on in British mathematics? Anybody know anything? They said, well, there's this guy up in Cambridge, Newton, and he's written this manuscript. So Newton would actually write this stuff up in a manuscript, but he wouldn't publish it. He'd just keep it. But occasionally, if you promised not to do anything with it, he would lend it out. And so he lends out the De Analysi. It's in London. Leibniz sees it and takes notes. Okay. Then in 1684, Leibniz publishes the first paper on calculus. Newton has not published anything on calculus, and this is it. So the world first sees calculus from Leibniz. And this is Leibniz's paper. Of course, it's in Latin. It's a nova methodus, a new method, he says. He's going to tell you. Here's the translation. The title says, a new method for maxima and minima, and also tangents, which is impeded neither by fractional nor irrational quantities, and a remarkable type of calculus for this. And there's the word that we still use. So this was the first publication of calculus. And if you look at this and see that it's about max, mins, and tangents, what kind of calculus is this? Differential. Yeah, this is differential calculus. 2 years later, he publishes the integral calculus and ties them together and becomes famous for giving us calculus. There it is. He's the first to publish. Now, in the 1690s, Leibniz, who's basking in his fame, tries to reestablish contact with Newton. And he writes and says, I write this rather that you should understand my devotion to you, a devotion that has lost nothing by the silence of so many years. So Leibniz is trying to reach out to Newton. And Newton responds, although it takes him 6 months, but he does. And he writes back and says to Leibniz, I value your friendship very highly and have for many years back considered you as one of the leading geometers of this century. So that was gracious. So they're on good terms. But behind the scenes, Newton is seething that Leibniz is famous for this discovery that Newton knows he did first. There's a 20th century author named Robert Merton who put it this way. He said, Newton, you will remember, had a way of not putting things into print until he was good and ready, and sometimes not even then. Right? All of this could have been settled if Newton had just published when he discovered things, but he didn't. And his contemporary, John Wallis, writes to him about this. He says to Newton, you are not so kind to your reputation and that of the nation as you might be when you let things of worth lie by you so long till others carry away the reputation that is due to you. And that's exactly what happened. So, in 1711, as this controversy grows and as Newton's anger grows, he writes to Hans Sloane, Newton does, condemning those who insinuate to their readers that the method of fluxions is the differential method of Mr. Leibniz, and do it in such a manner as if he was the true author and I had taken it from him. Newton knew that wasn't the case, and yet that's what the public thought. And one of Newton's colleagues, John Kyle, wrote to Sloane and sort of summarized it all in one nice sentence. Newton gave such clear and obvious hints of his method to Leibniz that it was easy for the latter to hit upon the same method. So that was the British line. Leibniz had gotten too many hints and stolen it. Well, Leibniz wasn't buying that. Here's what he said. I have indeed observed no shadow of an argument whence it appears that notice of the infinitesimal calculus came from Newton to me, for which reason we judge rather that it was not well enough known to Newton himself before I published. He learned it from me. I didn't learn it from him. And that was the counter-argument. Newton in 1716 writes to Antonio Conti, still grumpy over this original paper from 1684, where Newton's name did not appear in Leibniz's original calculus. Leibniz understood, therefore, in those days, that I had a method which did the same things as the method which he calls differential, and he ought still to acknowledge it. But he has lately attacked me with an accusation that amounts to plagiarism. Okay, now that year, Leibniz dies. And Conti writes to Newton and says, the war is over. No, not for Newton, it wasn't. 5 years after Leibniz's death, Newton writes to Pierre Varignon. And he says, Mr. de Mauve has told me that Mr. Bernoulli desires a picture of me. Now, Bernoulli, we'll meet him in a minute, but he was a stalwart for Leibniz. He was on Team Leibniz, right? He liked Leibniz. But he wanted a painting of Newton, and so he asked Newton. And here was the response. But he still has not acknowledged that I had the method of fluxions in the year 1672. So you're not getting a painting of me unless you give me that credit. So, the poor guy's dead already, but Newton's still upset about it. In that same letter, however, he does say to Varignon, I have always avoided quarrels. Okay. Well, now, I want to tell you about the greatest skirmish in this calculus wars. But let me first of all just tell you how we now view the controversy. And that is, we know that they each did this independently. Newton certainly did the fluxions before Leibniz did. So in time, he was first. But Leibniz did not borrow and steal this stuff. Whenever he saw the De Analysi, whenever he got the letters, the Epistola Prior and Epistola Posterior, he had already discovered the calculus. We have his notebooks. We have his notes. They were confirming things. And things like the generalized binomial series actually was new to Leibniz. But that wasn't fluxions. And in fact, the two both deserve credit. We're not, the war is settled. It's a draw. But it wasn't so back in the early 18th century. And the great battle that occurred, the greatest skirmish in the war, involves these two guys, the Bernoullis. These were brothers. They were very prickly. They didn't like other people. They didn't like each other. It was a great sibling rivalry. One was Jakob, the older brother. One was Johann, the younger. You can maybe see the family resemblance in the sneer that they have on. I like to say these are the kind of people that give arrogance a bad name. But this one, Johann, was the one that was Leibniz's champion, sometimes called Leibniz's bulldog. And he figures in the story. It involves what's called the challenge problem of the brachistochrone. This was a problem that Johann Bernoulli writes up in a journal, a challenge for the mathematical community. A new problem, which mathematicians are invited to solve, he says. And here it is. Assign to a mobile particle m the path AMB, along which, descending under its own weight, it passes from A to B in the briefest time. Okay, so you want to go from A to B down some kind of path. Which path gets you there quickest? And that will be called the brachistochrone, that path, because chronos means time and brachisto means least. So the least time descent. Johann had solved it. He had solved it using this new subject of calculus that Leibniz had taught him. And it's not a simple problem. He was very proud of it. But instead of just giving the answer, he's going to turn it into a challenge to see if other people are as smart as he is. So he publishes this as a challenge problem. Now, if you go upstairs, there's a brachistochrone exhibit sort of up there where you try to find the quickest route down the path from A to B, right up at the top of the stairs and to the right. I think it's called Galileo's something. Yeah, Galileo's. Get tracks of Galileo, yeah. So you can look for how fast you can get down there. Now, you might think right off the top, as I did the first time I heard this, that the quickest route down would be the straight line. Well, no, that's not it. And Bernoulli gives a hint. So he says here, to forestall hasty judgment, although the straight line AB is indeed the shortest between the points, it nevertheless is not the path traversed in the briefest time. And the idea is this. If you think about it, if I'm going to slide a marble down a ramp that's straight, it's going to start off going kind of slow, and then it'll get faster and faster. But suppose I have some kind of arc, and I let the marble go. It's going to start off going really fast because it's going almost straight down, and that early speed might be enough to beat the other guy to the bottom, even though it has further to travel. And in fact, that's what happens, as Bernoulli knew. So he says, however, the curve AMB, whose name I shall give if no one else has discovered it before the end of this year, is one well known to geometers. So this is the challenge. So he says the answer is a famous curve. It's not the straight line. Don't send me straight line. That's not it. And then see what happens. Okay, so the end of the year comes, and he's got one answer comes in from Leibniz. Leibniz could do it. But Leibniz says, Johann, you didn't give people enough time. You need an extension. So if you're students, you know this. If the paper's due Friday, you say, how about I get till Monday? So Leibniz suggests that Bernoulli resubmit the problem, restate it, and give people a couple more months to see who else can do it. So Johann does, and so he restates the problem. But then he says, if Easter passes and no one has discovered who has solved our problem, then we shall withhold our solution from the world. No longer. That's it, Easter. Okay, but then he can't resist writing some more in the journal. And he writes this. So few have solved our extraordinary problem, even among those who boast that through special methods they have extended its boundaries in marvelous fashion, although their golden theorems, which they imagine known to no one, have been published by others long before. That's a direct slam at Newton, who says nobody knew this, but other people had already published it. So that's in print, a direct attack on Newton. And then, just to be sure, Newton doesn't miss the point, Bernoulli takes a copy of the journal and mails it to Newton in London. So Newton can't say, I didn't get the problem. I didn't see it. He saw it. Okay, now, let's jump the channel. Now we're in London. Newton's niece was living with him, and she reports what happened. She says, when the problem in 1697 was sent by Bernoulli, Sir Isaac was in the midst of the hurry of the great recoinage and did not come home till 4 from the Tower, very much tired. He'd had a hard day at the Mint, and he comes slogging home. And there's this problem. But the niece goes on and says, he did not sleep till he had solved it, which was by 4 in the morning. So Newton got it. Now, somebody said this shows that he's getting old because the young Newton would have had it by 10, 10 in the evening, but it took him till 4 in the morning. But he got it. He writes the answer but doesn't sign it and sends it anonymously back to Bernoulli. Okay, now, what is the answer? What is the brachistochrone? It turns out the curve of quickest descent is the cycloid, a curve well known to geometers. And if you've done enough mathematics, you would have come upon the cycloid. Usually it's described this way. Suppose you have a horizontal line and a circle rolling down the line, and you just follow one point as that circle rolls. So a bicycle tire, and you follow the valve. So it'll go over an arch and hit, and then go over another arch and hit. And that's called the cycloid curve. It's a beautiful curve. It was of much interest in the late 17th, early 18th century. We still see it in bridges and things like that. It's very pretty. Now, of course, I can't roll down the hill that way. What you got to do is flip the cycloid underneath. That's how you get the brachistochrone. So if I want to go from this point to here in the quickest time possible, drop your marble down the cycloid. It'll beat all other routes to the bottom. That's a hard problem, even today. It's part of, it uses calculus. It shows up in a course on the calculus of variations today. But anyway, that was what the answer was. Okay, so now Easter arrives. What are the solutions that Bernoulli's got? He's got 5. One is his own, of course, because he wouldn't have done this if he couldn't do it. So One is from the celebrated Leibniz, his hero. One is from his brother, Jakob. I'm sure he was upset by that. One was from L'Hopital, who wrote the first calculus book. And one was anonymous, sent from London. Well, Johann Bernoulli was a pretty arrogant guy, but on this one he knew he'd been had. And so Bernoulli famously says, "Ah, I recognize the lion by his paw." That was Newton, had to be. So that's a very gracious comment. Newton wasn't so gracious. Newton's comment was, "I do not like to be teased by foreigners about mathematical things." So there. Okay, so Newton wins that skirmish. But remember, in the wars are a draw. They both get credit. And nobody's arguing anymore about who deserves more credit for the calculus.